Okay, so welcome back to another video. So here today we have a typical, algebra problem, solve for x, that sort of thing. And that's asking how many real solutions, I should say real, within the closed interval from 0 to pi, such that 81 to the power sine square of x plus 81 to the power cosine square of x is equal to 30. So I guess the premise that I want to, put out there is that this trick that we're gonna have to utilize for this following problem is you don't really see or hear teachers teach this method in a typical algebra course, whether you're in high school or middle school. Well, really high school technically. But the whole point is when you're finding for some variable x, it's not going to be as direct or straightforward than you think it's going to be, when you're dealing with, let's say, for linear equations, for example, or some sort of polynomials. That'd be easy to find some x value if you try to set that equal to 0. Well, of course, that's what we're going to do and get to that eventually, but you don't know how to deal with this, especially now that since we have that x are dealing with our exponent and then bases are the numbers, but also utilizing that we have trig functions, so things are going to get a little, the problem itself is going to make things use our techniques a little bit tricky, but that's not at all an issue because you want to use the the substitution method. So you substitute some part of a variable with a new variable, then solve it the way it is, then plug that back to help solve the original variable that you want to find for, and that's basically how this is going to go down. And it's pretty simple, especially now that since we have dealing with base, so we also need to utilize the facts of our knowledge with base numbers and utilizing with the exponents as well. But yeah, there's nothing much to it. It's just the substitution method is going to be the main goal, or I guess you could say the main meat of this video, because that's actually how we'll be able to solve this problem as well. So nothing more after that, so let's actually just jump right in. Okay, so if we're given this following, let's say we can actually rewrite the cosine square of x using a different form of a trig identity. And we want to do this so it'll make things a little bit easier on our end. So with the given, so I can write the same thing as 81 to the power sine square of x. Then I'll add this. So replace cosine square of x with the trig identity of 1 subtract sine square of x. And then set this equal to 30, right? Then if we just use the rules of exponents, we can actually write this in a form of a rational number, or rather in a rational function in this sense, since we have a variable. Then, so we have sine square of x over here. Then I can write this as 81 and then to the power 1, but then with the minus sine square of x, so that means that will have to be going to the denominator as well using that rule. So 81 divided by 81 to the power sine square of x. And so set that equal to 30. So here's the main part of what we're going to do. So we're actually going to do a little substitution, and we're going to say we'll call u to set that equal to 81 to the power sine square of x. So by doing so, we can actually just replace everything from our, the second line over here. So here we have u, and then add this with 81 divided by u, and then equals 30. Okay, so this is actually kind of a, well, not really kind of, but this is an easy way to find your variables for u. So if we just multiply u to both sides of the equation, so we have u squared, and so that's the way this will cancel out the u in the denominator from there. So u squared plus 81, but we have to do the same thing to the other side, so multiply u, 30u, and now if we just set this equal to 0, so I can just subtract the 30u, so u squared minus 30u, and then plus 81 equals 0, then you can see that you could actually decompose this into two binomial factors. This actually comes out nicely as u subtract 27 and then multiply with u subtract 3, set that equal to 0. Okay, then we would see that u is equal to 27 and u is equal to 3. We just plug the u back that we actually make that substitution of, and so we have two things we need to solve for. 81 sine square of x is equal to 27, and then another one is that 81 sine square of x is equal to 3. And so you might be thinking, how exactly can we solve for x from here? So of course I mentioned we can actually use our rules of the base and exponents. 81 can be rewritten in a form of the base 3, so that will be the same as 3 to the power 4, and then multiply by sine square of x. And then 27 is the same thing, can be written as 3 to the power 3. And then another one from here, so this is the same thing, 3 to the power 4 sine square of x is equal to 3, and then, to the power 1, so I guess I could just say that just for the sake of it. And then with the bases are the same, now we can actually set these equal to each other, so that means 4 sine square of x is equal to 3. So I'll just work myself ahead and do the same thing over here. 4 sine square of x is equal to 1. Then we just divide 4 on both sides, so we now have sine square of x is equal to 3 divided by 4. Over here, sine square of x is equal to 1 divided by 4. And then we just take the square root of both sides, so we have sine of x. And so this will be equal to, so we have to deal with both the positive and the negatives when we're dealing with the radicals. So it'll be plus slash minus the square root of 3 over 4. Then same thing over here, or not sine squared now because we already took the square root. So sine of x is equal to plus or minus 1 over 2. And then now it's easy to see that you could just take the inverse sine of both sides, and if we just look at our, radians or the unit circle, whatever helps you find like the, the radians, then you'll notice that for both the positive and the negative values that we take the inverse of, we'll see that for x over here, x is going to equal 4 pi divided by 3, 5 pi divided by 3, and those two radians are specifically evaluated, plug into here to get the negative square root of 3, and that's supposed to be over 2, like so. So divided by 2, okay. And then you have 2 more values, but those are dealing with the positives for the square root of 3 over 2, and that'll yield pi over 3, and then 2 pi divided by 3. And then for the following over here, x is equal to, so we would have 7 pi divided by 6, 11 pi over 6, and those 2 radians will give out for the negative 1/2. And so the last 2 will give out the positive 1/2, pi over 6, and then 5 pi over 6. So we have those values of x, but notice that x has to be in the closed interval from 0 to pi. And obviously you can see from 4 pi over 3 and 5 pi over 3, it does not fit in that set. So we can just disregard these 2 values. Same thing for over here, 7 pi over 6, 11 pi over 6, they're not in that closed interval, so disregard these 2. And so we're just left with these 2 values. So that would have to mean that the final answer, so I'll just write this again one more time, x is equal to pi divided by 3, 2 pi divided by 3. Let me write this a little better. So we have pi divided by 3, 2 pi divided by 3, pi over 6, and then 5 pi over 6. And so to answer the question, how many solutions? Therefore, there are 4 solutions that satisfies the equation. And just like that, we are done with the problem. And let me switch to different colors. This makes sense that way. I'm not using the same thing. So here we have our 4 values, and then there are 4 solutions satisfying the following trig. And it really comes to show that the substitution method, just like here before, I'm sure a lot of you guys, if you're trying to solve for this problem, for example, even if you're pretty like well versed in finding solutions for x, whether it be linear or polynomial, but in a sense of this situation, you would never, I'm sure like you would never think of using this method. So this is actually just one clever trick to utilize if you're trying to solve for some sort of like variable, as given for this example. There's like a whole class of family of functions like very similar to this example that you would need to utilize this following. So yeah, that's pretty cool if you ask me.